In this lecture, we're going to continue our introduction to parametric equations with two specific goals. First, I want to give you some more insight into the additional benefits that we get from adding a parameter to our equations. And second, I want you to see some of the unusual graphs that parametric equations let us create. Things that would be really difficult, sometimes even impossible, to do with our kind of traditional rectangular equations. These equations should look very similar to the last set that we looked at in the first lecture. X equals cosine theta and y equals sine theta, only with a multiplier added to the theta parameter. So let's start off collecting some points and see what we end up with. So I'm going to go ahead and graph these, and I'm going to do kind of the same thing I did last time. I'm going to use 5 grid lines here to represent one unit. That'll make it kind of easier to see what's going on. So 1 comma 0 is going to be here, and negative 1 comma 0 would be over here. 0 comma 1, let's see, is up here. And the other two, let's see, 0.5, 0.866. 0.866 is actually pretty high up. And 0.866 here. And there's our curve. Now, if you think back to the previous lecture, we used these same 5 values, but we got just a quarter of a circle, where here those 5 values got us halfway around. And of course, if we continue calculating values, we'll get back to the starting point with these equations when theta equals pi, where the original example with just theta as the parameter didn't make it all the way around until we got all the way to 2 pi. So this example illustrates one of the additional benefits that we get from parametric equations, where a rectangular equation just gives us the shape of the path. The parametric equation gives us both the shape and, if we think of the parameter as representing time, a way to talk about how fast an object navigates the path. So we could plot this by calculating points like we did in the previous examples, but I'd like to try a different approach here and see if we can reason out what the path will look like based on what we already know about the graph of x equals cosine theta and y equals sine theta. So first, let's use some trig identities to simplify the two equations. The cosine of negative theta is equal to the cosine of theta, and the sine of negative theta is equal to negative sine of theta. So the x-coordinates are changing exactly the same way as they did with the original graph, but the y-coordinates are all going to have the opposite sign. So this means that where the first graph went to y equals 1/2, this one goes to negative 1/2. Again, I'm counting 5 grid lines as one unit. So where the first graph went to y equals the square root of 2 over 2, this graph goes to y equals negative square root of 2 over 2. So ultimately, this will give us the same visual result, but again, thinking of the parameter as the time, an object following this path will be going in the opposite direction. So this gives us another additional piece of information that we can get from parametric equations that we didn't get from rectangular ones. We can also see the direction that an object is moving along the path. The second interesting thing we get from this new method of defining an equation is that we can generate some unusual graphs like the ones here that we could never get using our traditional Cartesian functions. The hypotrochoid in the middle, for example, is the path made by the end point of a stick that's fixed to a small circle as the small circle rolls around the inside of a bigger circle. Now, if you're following along on the White Crane Education website, there are some laboratory areas where you can experiment with the two parameters, like the 1 and the 3 here, that determine the shape of a Lissajous curve. Now, to give you an idea of the source of these equations, I want you to take a closer look at one called the cycloid. The curve starts with a circle and a point on the circle. And I want you to think of this as a tin can sitting on the x-axis. And if we start the can rolling along the x-axis, the curve traced out by that point is called a cycloid. So let's see how the equation for a cycloid is derived. Right? First, I want to be clear what my goal is. Right? My goal is to find equations. There's going to be two of them, one for the x-coordinate, one for the y-coordinate, for this point, right? An arbitrary point that I picked on the cycloid. Now, to do that, first I need to fill in a few values. Let's call the radius of the circle r, and let's call this central angle here theta. Right, and we need to be clear now, r is not a parameter. Theta is going to be our parameter. R, the radius of the circle, is not going to change. The circle isn't going to get bigger and smaller as it rolls along the x-axis here. So theta is going to be our only parameter. So now, before I go up to the coordinates of my point here, first I want to get the coordinates of the origin. Right? And to do that, let's think about this x-axis distance. It's going to be my x-coordinate. This distance is the same as the length of this arc. Or you can think almost like that arc is the x-axis peeling away as the circle rolls along the x-axis. So the length of this arc is r theta. We're assuming, right, that theta is in radians, which means this length is r theta, which means the r coordinate of my center is r theta. And the y coordinate, well, that's this distance here, but that distance is just the radius of the circle. So the y coordinate is r. All right, and this is going to give me what I need. Now, to do this, I'm going to start by drawing one little extra line. I'm going to draw a line from my chosen point, and I'm going to draw it over to that vertical radius. And the reason I do this is this makes a right triangle. All right, so now let's see if we can't fill in some sides here. Right, the length of this side, applying just a little basic trigonometry, the length of this side is r sine theta, and the length of this side is r cosine theta. All right, and that's nice. That gives me what I need to find this height here. That height is the y coordinate of my point, right? The point that I'm trying to locate. So if this distance is y, this distance, remember, this is the radius, r, then what do I have here, right? I have these two little segments that make up the radius. So I know that r cosine theta plus y is equal to r. All right, so if I solve this for y, I get y equals r minus r cosine theta. And there's my y-coordinate formula. Right? You could explicitly write this as a function if you like. You could actually write this y of theta equals that formula. All right, so that's half our problem, right? We found the y-coordinate. Now I need to find the x-coordinate, and I'm going to use a similar trick. I'm going to drop a new line straight down from my point to the x-axis. So why don't you pause the presentation here, see if you can work through kind of the same reasoning and figure out what the x-coordinate of our point is going to be. All right, so here's what I'm going to do. This distance here is x. That's the distance that I'm trying to find. That's my coordinate. This distance here is the same as the distance I added to my triangle. This is also r sine theta. So I'm going to use the same logic. I'm going to say, look, x plus r sine theta equals r theta. And if I solve this for x, I get x equals r theta minus r sine theta. And there's my second formula. Right? There's my x-coordinates. So I've rewritten these here right? Kind of neaten them up a little bit. They're commonly written the way I have them on the second equality there, with the r's factored out. So those two equations there are the parametric equations of a cycloid based on a circle of radius r. All right, so now before we go any further, I want to take a step back. So I said at the beginning, way back in the introduction to the course, that I wanted you to think about things not just as individual questions, individual problems, but I really want you to think about the thought process that goes into coming up with these formulas. All right, so what I did here, what was going on in my head, was first I said, look, I need to clearly define the problem. What is it I'm trying to find? And that was the first thing we talked about, right? I said I'm trying to find the coordinates of this point. All right, and then I said, well, look, I know the radius, and I've got this central angle. And I said, look, I've got angles and distances. If I can bring triangles into this, then I can start applying some trigonometry formulas, some trigonometry definitions, and see if I can't fill in the distances, right, and end up with the distances that I needed. So that was kind of the thought process that, in my mind, went into creating this whole solution. All right, so now that we've seen some parametric equations, seen how some of them are defined, and looked at some basic examples, in the next lecture in the series, we're going to look at some more examples and use them to illustrate some of these additional advantages that we get from our new tool.